So, on that flash drive, you have a total of 13 lessons that come from Solidworks. So if you want to work after this class, or when we get into next week, you'll have all that material. But for now, we'll just do 2, 3, and 4. Lesson 1 talks about how to use a computer, how to click on windows, how to open and save files. You guys don't need that. So we'll go ahead and move on to section 2. So as we start looking into lesson 2, we're going to talk about what's important when it comes to robotics at least. Most of what SolidWorks does is broken up into 3 things. They have electrical components and other modules, but for the main SolidWorks, and we're talking about designing mechanisms, you got 3 things you want to do. You got to design parts, you got to group those parts into assemblies, and in the end, you have to make a drawing. And when we say drawing, we don't just mean a little doodle like we do the drawing on the back of a napkin. A technical drawing defines a part so that you can set it off in the machine shop and get back exactly what you need. It conveys all the technical information about what you need to make. As I understand it, you guys don't need that. You normally send the model to Georgia Tech and you get a part pack. If you were to go to a real machine shop or pay somebody real money in the regular business world, it's almost always defined by a drawing. So even though we don't have to focus on the drawings for robotics, moving forward, years from now, the drawing will be more important. But for now, we're worried about mostly parts and assemblies, because you have helpful people at Georgia Tech with machine stuff from the parts and the assembly drawings. So, an individual part, if you take this little Lego block looking piece and this one, you can assemble them together into an assembly. You have constraints that define how they get mated together. It's kind of intuitive. You take 2 Lego blocks and snap them together, they only really go together one way. But if you have objects in space that aren't really defined, because in the end, these are basically perfect Play-Doh extrusions. If you can make Play-Doh perfectly straight and perfectly round, that's what you're doing. You're doodling in space and you're making things by either adding material or removing material. In fact, a lot of the commands that you use a lot are called extrude. Just like the old Play-Doh maker where you pile a piece of dough in the back and you push on the handle and you extrude out round and square shapes.
Toothpaste.
Yeah, toothpaste. So, ultimately, you'll end up doing part drawings that explain how to machine this thing to give you the part that you need. Or, you'll have a group building a robot for you. Perhaps you're not in the same place the robot's getting built. And they'll have to use an assembly drawing, which shows them what it looks like, and it'll have a list down here of all the parts they need in order to screw this thing together and make what it is you're making. So you have 2 different kinds of drawings, whether you're documenting a part or documenting an assembly. When it comes to these features, we talk about different features common to SolidWorks, and there are about a dozen of them that are common that most of the world uses, and most of them represent something that a guy can do in the machine shop, machining operations basically. And we'll go through those here in the first lesson. We'll talk about what it takes to define this part. It has lots of different types of features. As you go through the lessons, if you follow this, you have a student guide, so that if we had more time, you guys would be following along with me in SolidWorks as we're working through this. And all this is explained for you in those presentations. But when you build a part, it's all chronological. And so you can take a big blob, and that'll be your base part. And as you start refining it and adding features, they start to stack up. And you get this chronological history, where feature 3 is built off of feature 2, and feature 4 is built off of feature 3. And sometimes they reference earlier ones. And so you can change an early feature, and it will change all the downstream stuff. If you have a big part with a bunch of stuff hung off of it, and you go back later and you resize it, make it smaller, all those other features on it are going to shrink too. And giving some forethought to how you organize those things is a big part. Once you guys get good at using SolidWorks, you start to learn what's important when you define features relative to each other. So that if you resize or change something, and you find out later you need to stretch a part, you don't want everything else to break. And that'll become clear later. So these features define the shapes and operations that construct the part. So if we look at how to build this thing and all these steps in the feature tree, that's what this is called, the feature tree, that chronological list. We're going to start with a base part. So if a guy were to go to, you guys have heard McMaster car, where you guys will order a lot of material. You get a McMaster car and you can buy a big long strip of steel that somebody can cut to length. For a little bit of extra money, you get McMaster to cut it for you. So you can maybe order end parts that are ready to go when they come into your robotic shop. But you can order a piece of steel that's 2 inches wide and 1/4 inch thick and 4 inches long. and have something to start with, and that would be this. So you have a base feature that's created from a 2D sketch. You basically sketch a rectangle and then make it a 1/4 inch deep or something. And that would give you your 3-dimensional piece, just like extruding toothpaste. And then on that, you'll add the rest of these features. So if you were to build that part of the roof you're talking about, you would add a little blob at the top and a bigger blob at the bottom before you then start making other changes. So what we call, this is called the boss feature, and we'll get into that later, but you'll see how they add on. So you have that part, and you're going to add the cut out at the top and a cut out at the bottom. So you can add a little semicircular cut at the top going all the way through, and add a rectangular cut at the bottom that goes a little bit of the way in. So you'll have to define these cut features, where a guy on a machining a piece of equipment can cut those for you and make those shapes. Then you'll go and add some little screw holes on the side, because you're going to have to bolt this to something. We'll learn how to do that. We'll learn how to round off these edges. That's important so that nobody gets cut, because when you machine these metal parts, they're very sharp. So whenever you get the opportunity, if you have an external feature that could rub up against somebody, you want to go and knock that edge off and round it. Same thing down here. And then what we call a fillet feature is another name for a radius. And then a chamfer is this little guy, a little 45-degree thing just to knock the edge off. If you were to slide a shaft in that hole, before you add this, if you were to have a shaft you want to pass through that hole, it'd be hard to get in there. If you bevel the lip just a little bit, you can slip that shaft in. So it's a common feature you come across when you're making machine parts, is adding something like a little chamfer. So in the end, you have this part that's made off of each of these features one at a time that we were talking about. And all of your parts are going to be designed that way.
You kind of skipped over fillet pretty quickly.
We did, so a
Like
fillet.
that.
Well, you have a couple of different kinds of fillets. So when you go from this part to this, you're adding these external rounds, these fillets. But you can also, it's impossible to make this perfectly square cut. If you imagine, if you had a piece of steel in front of you, and somebody would have told you to make a rectangular cut in there, how would you do that? Because if you take a drill, and you drill into that thing and drag your drill across, you'll get a long rectangular cut, but you'll have round ends because of a round drill bit. So normally, instead of just having radiuses on the outside, here and here, you'd have a radius on the inside here. Because otherwise it's not possible to really make this, at least not without doing some very expensive processes. But that's not terribly important right now. We'll get into that in the future. You have fillet, chamfers. And so everything starts with a sketch. You start with a 2D profile. You define what your shape is going to be, and you define how far you're going to stretch it. Whether you're creating an extrusion, or if you're removing material from that and making a cut. So you have sketch features that you define, and you have operation features like the chamfers and fillets and other things that you apply to other features that have already been defined. So if we were to design this part that we just talked about to begin with, and you guys, when you start filling with Solidworks, you have an example of what this part looks like, and you can see the feature tree that we're showing in this assembly. But you would start by sketching on a plane. So you've got 3 planes, an X, a Y, and a Z. And it defines basically the orientation of things in space. So you're going to sketch on one plane a rectangle. So you'll sketch this profile. You have to define it and make sure that the length and the width and the angles and everything you need from trigonometry, to define a triangle. You learn all of your triangle definition, your side, angle, side, and all that kind of stuff, what it takes to constrain a shape. The same things apply to this. So you got to design features that are defined, and once you know how big this rectangle is, and it's all clear to SolidWorks, then you can stretch it, and you get yourself a blob of material that you can start with. So in the end, once you're done extruding this thing, you end up with this perfect piece of clay or extruded material. And then the other common way to make shapes is if it's something that will be round, turned on a lathe, if it's I have a really good example. You have parts that are stretched in space or parts that are rotated in space to define that volume. And it's how machine equipment works. If you go to a machine shop and you get something made, it usually comes off of either a giant drill that cuts rectangular pieces, or a giant spinning lathe that cuts round
So
pieces.
you have it spinning and then you make cuts while it's spinning.
Yeah, so you can imagine if you have this thing, or when you see somebody barbecue a pig, you put a stick through the middle and the pig turns over a spit. Well, if you were to spin this thing in space and draw along the edge, you would remove that material, and you end up with something in the shape of a bottle. If you're making this out of steel, if you had parts for your car that your wheels are going to turn on, you would start with a big block of steel, spin it, and remove material so that what you're left with is round but has some shape to it. So in this case, you have something like a candle holder, a chess piece. You can imagine if this were your axis that you're going to rotate about, and you spin this around, you'll get something that looks like a pawn. Or in this case, they're doing a candle holder. So you have to define all the little shapes that make up that sketch, and then you tell it what axis to revolve the sketch around, that center line. You tell it to spin, and you end up with something that looks like this. So as far as terminology, so that we're all speaking the same language and we're talking about all the same kinds of features, you've got your feature manager on the left that has a list of all your datum planes, which are those planes you sketch on and the directions that you extrude in. Your big long list of features, starting with your most basic, and then as you refine it step by step. And then over here in the graphic area, you can determine how you represent it, whether you color it and paint it, whether you want a part you can see through, because in an assembly it's important to see what's inside of it or what's behind it. So once you get into the interface, you can see that this is what we call a 3-projection drawing. It has the front, top, and side view. It represents this thing that you've drawn in space. So that's your part window and your drawing window. Normally you only have one open or the other. In your property manager, this is one of the things you'll struggle with early on, because these are the steps it takes to define. What it's going to do is Solidworks will tell you what you need. If you think you've drawn a rectangle but something is left undefined, Solidworks will say, I can't do anything with that. You haven't told me exactly how long or how tall your rectangle is, or how long you want to stretch it. And it'll tell you what it needs. And so this is a little conversation you're having with SolidWorks to define what it is you're going to ask them to build for you. So inside your property manager, it'll ask you questions, it'll define. In this case, what they call a blind extrusion is saying, I'm not going to stretch this thing until it touches another feature. I'm just going to tell you how long it needs to be. That's the most basic version. And when it's colored blue, that's the same, that aligns with this little blue arrow. If you were to drag this out and make it longer, or put in a bigger number, this part stretches to show you dynamically what the result's going to be. It's kind of like a preview of your definition over here on the left. So an axis is any single direction that you can stretch something along or spin something around. You have a plane, or some of you here call it a datum, but a plane is just a flat surface that is usually your starting point. Or if you're working off of a rectangular feature, it's another phase that you're going to reference when you're stretching these things and defining them. And planes actually have a second use. When you go into assemblies, it's oftentimes easy to assemble things to certain assembly planes. So it's not just used in parts, it's used oftentimes in assemblies. Your origin is everything is referenced to that origin. If a part is 2 inches long, it can be 2 inches long from the origin, or it could be 1 inch in each direction from the origin. 1 inch left and 1 inch right, you end up with the part 2 inches long. And as you define parts, that'll become clear. One of the good things about the student version, of course, is you guys can take these home. Of course, these are Meggitt laptops, but you guys can install all these on your laptops at home, and you can fiddle with this over the course of 2 or 3 nights. You can get pretty good at this, honestly. And you've got all the support you need from the SolidWorks tutorials to build these parts once you go home. So you have faces, and on this part you've got some short, long faces that are along the length of the extrusion. You got one big flat face that is the sketch that you made and stretched. You've got another round face here that popped up when you stretched that round feature. So So you got a couple different faces, and you use those when you're defining relationships and assemblies and that kind of thing. You have edges, of course. You imagine you all know what an edge is. If you're going to later build this part, like we were saying, knock down some of the edges and nobody gets cut, you would say I want a 2-inch radius along this edge or along that edge. Or if you pick both, if you pick this edge and that edge, you'll get a rounded corner so that nobody hangs up and gets cut or chews up their clothes or whatever. And then of course vertex where the two edges intersect. Most of which, I think you guys have seen all this stuff in geometry or the trig. So your base feature is almost always going to be either a shape that you've extruded in a straight line or one that you've revolved in a circle to make your base feature. But everything else is based off of it. And by default, it's called extrude 1. If you ever get a lot of complex shapes and you're trying to remember which feature is which, you can rename them to features. It doesn't have to always be extrude 1, but by default, that's what it starts at. So normally, if you're going to build a rectangle, which most parts are based off of, and you got to start inventing things in space and dreaming up what your part is going to look like, you usually start with a rectangle. To that rectangle, you can add fillets and radiuses. You can shell it, which means basically, I'm going to cut away the top side and leave a thin skin of what is left of that material. So if you were to try to build this thing that's a bathtub shape, you can draw 2 rounded rectangles and stretch it to make it tall. You can draw a big solid blob and tell it to shell, to cut out the inside. There's a couple different ways that you would make a given part. And it's funny, when you start exchanging parts, you'll see the different people design things different ways. It's kind of weird. You can almost get into somebody else's head to see how they think. When you would expect to get a bathtub part in, and the guy made it totally different than when you thought, maybe they made it like a piece of sheet metal, and then bent it up and closed on the end, and you think, what in the world was he thinking? He could have just designed a blob and shelled it. 2 steps and you're done. But what you do is you go back to that guy and explain. I think you wasted a lot of time making it the way that you did. But you guys will get better as you go back and forth with these kinds of things. And then you can add a hole that goes through the length of this thing. Maybe you're going to hang on a pin. Maybe this is going to scoop up balls on your robot and learn to pivot like the bucket on the end of an excavator that's moving dirt. In fact, this is going to be one of the parts we define too in our lesson 3, the second one we're going to do. So normally, like we said, you start with a rectangle, you extrude it. By default, the extrusions are all perpendicular. You can extrude in different directions, but normally you define a shape in the X and Y plane, and then you extrude in the Z plane. And then to that box, you can add fillets, and you do that by picking the edges that you want to round, telling it the radius that you want, and then it'll round all the edges for you. If you were to make a dice, or a die, when you guys throw a dice, it's a little cube. But it's not a perfect cube, it's not sharp. All the edges are knocked down. You got a small radius on all those edges. So you could pick 4 of those edges and get kind of a rounded off dice. You can pick all 8 and get what you normally associate with a round die. All 12.
16.
Now I think there's 12 edges on the die. We can figure it out. So if we're going to make this box originally, so what we've done is we've stretched a rectangle to make a rectangular block. We've knocked down the edges with a fillet. And then we're going to pick the face that we want to remove material from. We're going to make that bathtub shape with a shell feature. And then we got to put that pinhole that goes the length of it that we're going to hang it from. Defining the wall thickness when we shell it. And you can only apply a shell if you tell it what the wall thickness is going to be. As part of the definition. And if you want it thicker on the bottom than it is on the top, you just have to go back and add material or pick some special features. But by default, all of your walls end up the same thickness. You just have to tell it what thickness you want and it'll do it for you. And then you want to put this cutout going through. Now, you can add material and make a pin that goes through here, just like if this were clay or Play-Doh. You can have a bucket with a solid pin to the middle. But that's not what we want in this case. In this case, we want to remove material. So we're going to sketch a big long cylinder, but instead of adding material, we're going to remove material. And that'll make a big long hole through the thing that you can put a pin through. So you'll define the 3D sketch of where that hole is and tell it to extrude in that direction. But instead of adding material, you're going to remove material. You'll end up with that pinhole going through. We'll learn about some of the dimensions and how you reference things. For instance, if you were to say on this part, instead of saying it's 40 millimeters from the bottom, if you were to say it's 20 millimeters from the top, that's still a good definition. It means that if you were to make this box a little bit shorter, if you were to bring this edge up a little bit, your hole would move relative to whatever side it's referenced from. And there are a couple different ways to define all these different features when you're doing these. You can also go back later and you can change the size of the hole. You can change the distance from the hole to the edge. So you can move all these features around even after you've defined them. And if you wanted to, we're not going to do it, I don't think, at all in robotics. You can also define them by equations. You can say, I want the distance from the center of the hole to the edge to be half the length of the edge. That way it's always in the center. There's an easier way to do that. You can just put it on the center. But if you want to write formulas, if you always wanted a hole that's a third of the way from the edge, you can do that too. You can define it as a fraction of some other feature or write other equations. But frankly, it's a pain. And those geometric relationships are what control the behavior and the definition of that feature. Oh, here's another thing too. When we talk about design intent, what you want to do is you want to design in such a way, and you'll learn this if you guys aren't seniors. If you're a sophomore or a junior, and you're going to see these designs carry over when you're the next. You'll want to reuse parts. You don't want to start from scratch every year. So what you want to do is you make it clear what it is you're thinking and how you design the part, how you got what you got. And you want it to be obvious by the person following behind you why you define things certain ways. It makes it a lot easier for them to reuse your design. So one of the things we do when we're defining these parts is you have to define shapes. You have to give them dimensions. And these things will show up on drawings. In this case, you have a base height or depth of that part that's 50 millimeters. The top is 25. You can change that so that you can manually change to 150, or you can define this one as always being half of that one. So when you rescale one, the other one grows automatically. Which is what they said here. They said that the boss depth is going to be the base depth divided by 2. So this will always be half the height of this one. When you're defining these relationships in a sketch, one of the big ones that's always assumed is orthogonality. That if you draw a flat bar and a vertical bar, it's going to throw a 90-degree angle between the two. Because most of the world is built on right angles. It's going to assume, unless you tell it otherwise, that everything's a right angle. If you want a different angle, you got to go kind of out of your way to make it, you draw a 45, and then later on give it an angle and define exactly what that angle is going to be. But when you go and sketch these things, it assumes if you draw a roughly horizontal line, it'll define as being horizontal. Because most of the world is built that way. If you want it makes a lot of assumptions to speed things up for you. If you want a diagonal line, you'll have to make it clear and undo. If you draw something that's roughly horizontal, but maybe you try to draw it at a 5-degree angle, it'll probably assume it's horizontal. And you got to delete that and tell it, no, I didn't want horizontal, I want a 5-degree angle. But it'll assume most vertical lines are straight up vertical, horizontal lines are absolutely horizontal. If two lines cross, it'll assume an intersection. If you already have one line, you draw another one that's in the same direction, it'll assume that the two are parallel. So you have to go out of your way to make them different directions if you don't want them parallel. But if you don't like the assumption that Solidworks makes for you, this sounds like a pain, but it really does speed you up. If it assumes two lines are parallel, they almost always are. It saves you a step. But if you don't like that, you can go back and delete it. You can say these two lines aren't parallel, they just happen to be roughly the same direction. But you can go back and change that. It also assumes, like we said, that most angles are right angles at 90 degrees, but you can always go back and change that. If you draw two circles that are very close to being concentric with each other, it'll assume that they are. And again, you can change that. So you also have things like, if you have a line going into this radius here, it'll assume those two are tangent. Because if they're not, it's hard to define that geometry without it being tangent. It'll assume two circles that touch are not going to be, oh gosh, what's that?
Good.
No, I know that. No, I'm trying to think if you have Tom, Mary, and the things that Tom and Mary both enjoy.
Oh, the Venn diagram.
Yeah, Venn diagram. This is going to assume you're not drawing Venn diagrams in your sketch. If you have two circles that are almost touching, it's going to assume they're tangent. So if you're a sloppy doodler, it'll go ahead and close it. It'll make some assumptions to try to speed you up. Same thing here. We have these tangent shapes. So within the Solidworks window, when you start something new, it'll assume generally you're going to design either a part or an assembly or a drawing. You can have some base parts where, like here at Meggitt, you have a bunch of engineers that are all doing different things. But in the end, they're all going to use each other's parts. So you can assume that everybody's going to work in inches, everybody's going to work in millimeters. You're going to assume that their unit of mass is going to be pounds versus kilograms versus newtons versus moles versus stone, any number of things. You can decide that everybody can use the same drawing board. So you can have start parts that basically define a lot of those things. And for your case, I don't think it's worth worrying about. If you guys ever want to get specific, you could do that. You could decide that everybody's going to start with the same part and use the same units. But for the time being, the default is generally good enough. And that comes up here when you have templates. So it'll control the units, tabs, and other things. For the time being, I think we're also going to use inches, pounds, and seconds. They're all IPS system, even though the rest of the world doesn't use it. Those are your hardware. If you go to McMaster-Carr, if you go to Ace Hardware, if you were to buy a 1/4 inch bolt, that's cheaper than a 6 millimeter bolt, just because it's more common. When it comes time to, it's not so much about cost. In y'all's case, you're going to get parts quickly. You're going to find out the day before a competition that you want to change a wheel and you need a screw to go through it. You're going to wish you could go down to Ace Hardware and get a 6 millimeter screw, but you can't. So you're going to wish you had designed for a 1/4 inch screw, which is the same, roughly the same size. So most of what you guys will be designing with, at least from robotics, is going to be in inches, pounds, and seconds for your units of measure. And if you're doing the document properties, you can always change that. You can change your units of measure if you wanted to. And there's lots of things that you can do in your properties. You can change the default colors, you can default units, text sizes, any number of things. But for robotics, it's not something we're going to worry about. Because in the end, you guys don't have it's 5 days from the kickoff until you want to have at least your prototype design laid out, is that right? What is it that's done in the first 5 days? What is it that you guys do in the first 5 days? Like from the kickoff in that first week?
So, like, you get your general like division for the robot drawing, and your, like you said, the prototypes that we may or may not use.
Okay, so do you end up cutting parts in those first 5 days, or are you looking at design
Prototypes, I
alternatives?
would assume, yeah.
Okay.
That's fine.
Do you start with an old robot that you cannibalize your parts quickly, or do you normally start from scratch?
Normally we start from scratch, but yeah,
Okay.
we start with building, we start from scratch.
So, you'll forgive me, we just don't have a lot of time, and you're not gonna be using a lot of these. Because you guys will be moving pretty quickly in those first 5 days. So normally, you have, just like you have in a drawing, you can define the top, bottom, front, left, right views of a part. You can also do the same thing when you're designing the part. You can have 4 windows open and see all 4 sides of the part. But if you're using a mouse, it's easy to drag with your middle button and spin the thing in space. So you can get to whatever side you're working with pretty easily. You don't normally need the 4, what we call orthogonal views. But if you want to use that, you can. It's an option for you when you're designing parts and assemblies. So, when it comes to defining a sketch, you'll have to pick the face that you're working on. Is something here? Or is that just the wind blowing away? Hey, Brendan. as we get into the parts, they'll start with a sketch to extrude. You guys have already heard this 3 times. You don't really hear it a 4th time. But this is the way it actually looks when you're using SolidWorks. You'll start with the origin in the middle of the screen, and you'll pick a point and you'll stretch it to make a rectangle. Do you guys have SolidWorks open? You want to try filling with this as we're talking? So if you can start with a fresh sketch, in fact, I guess we can do it this way. Up in the top left corner, you've got this option for a sketch. Unfortunately, I have SolidWorks on this computer that's on the projector. If you start with a new and then part, up in the top left corner, SolidWorks has gotten good over the years. It's gotten to become such a complex program. It's got thousands of buttons. So what they do is they scale it down. They only give you the buttons that are appropriate for what it is you're doing. So when you pick sketch, you'll get the options for just that sketch. And what happens up here, what they call a ribbon bar, these commands will change based on what it is you're doing. It's not going to show you all the commands in the world, just the ones appropriate for a sketch. But if you sketch a rectangle, you can left click here on the origin, and then stretch it out and left click again to define the size of your rectangle. If you wanted to have a rectangle that's centered on the origin, you can pick a center rectangle, where you pick the middle, drag out to a side, and it'll give you a rectangle that's centered on there. Personally, I like to work that way. We'll talk about why here in a little bit. And then you left click on the top right hand corner, and you've now doodled out a rectangle. You haven't defined how big it is there, so you got to go back now and define it. So once you click on once you've clicked out your rectangle, and it's time to define how long it is, you click Sketch and Smart Dimension. And that'll give you a chance to click on the upper leg or the right leg and drag those out and give them a dimension. You define how long those legs are.